Between gamma rays and ultraviolet, we find X-rays. In 1895, just before Christmas, Ronton, working in his lab in Vienna, discovered that cathode rays were producing radiation that affected photographic film. He found a way of seeing inside our bodies, and within 6 weeks, images like this were being produced. X-rays can pass through materials, like our skin and tissues, which visible light cannot get through. This is because they have a higher frequency, and so they transfer more energy. Let's sneak forward a little while and have a peek at what's coming in P3. Let's take a look at how X-rays are made. The cathode is heated. This emits electrons by thermionic emission. The positively charged anode is really positive. 100 kilovolts are used so that those negative electrons are attracted and accelerate across. The vacuum makes sure that nothing gets in the way of those accelerating electrons. That positive anode is made from a tungsten alloy, so it's got a really high melting point. The accelerated electrons crash into it, and their kinetic energy is transferred to the tungsten atoms, causing them to emit X-rays. Now 99% of the energy from the electrons is actually transferred to thermal energy and only 1% to X-rays. So the anode can get really hot. We're talking about temperatures around 2,500 degrees Celsius. So that's why it's rotated and cooled. The radiographer can change the potential difference, and so they can change that accelerating voltage, which means they can change the kinetic energy of the electrons. The higher the voltage, the greater the kinetic energy, and the more energetic the X-rays. So the X-rays that are produced with a shorter wavelength, a higher frequency, and they would be more penetrating. The radiographer can also change the temperature of the cathode. The hotter they make the cathode, the more electrons are emitted by thermionic emission per second, and that means the more X-rays will be made per second, so there'll be a greater intensity of X-rays. Doctors and dentists use X-rays to produce shadow pictures of the body. Bone is more dense than tissue, and so it absorbs more X-rays, leaving less to get through to the detector, and they're the areas that appear white. The grey areas show where more X-rays have been transmitted through the less dense tissue, and the darkest black areas, they show where lots of X-rays have made it to the detector. So broken bones show as a dark fracture in the white image of the bone, as more X-rays have been able to get through the break. This imaging is taken further in CT scanning. Inside the scanner, lots of 2D images are made at different angles as the X-rays rotate around the patient. These slices are then used by the computer to build up a 3D image. Fluoroscopy is another medical use for X-rays. This method produces a moving image of the patient. So in the picture here, the person's having their stomach or intestines checked. They're drinking a liquid that contains barium. Barium will absorb more X-rays, and so it appears lighter on the X-ray. The X-ray source and the detector stay in the same position in fluoroscopy, and the moving images of the patient are obtained because the patient's exposed to X-rays for many minutes while the moving pictures are recorded. This then is turned into a video of the X-ray that shows the patient's organs working in real time. Away from hospitals for a moment, airport security use X-ray scanners too. They use them to identify liquids, explosives and metallic objects. In some food factories, X-rays are used to check there are no unwanted bits of metal or stone in the product. And X-rays can also be used to check the internal structure of objects, like engines, Make sure there's no loose components or fine cracks. X-ray crystallography is a use of X-rays to image the structure of crystals in 3 dimensions. X-rays are ionising. This means they can damage the DNA of cells, they can cause cells to mutate, and so X-rays can cause cancers. Radiographers wear lead aprons and stand behind a lead screen or leave the room to minimise their exposure. A chest X-ray will expose the patient to a dose of radiation equivalent to 3.5 days of background radiation. A CT scan of the same part of the body would increase the dose to the equivalent of 3.1 years of background radiation. And so when deciding which imaging technique to use, doctors have to balance the risk. In airports, X-ray scanners use a much lower energy level X-ray, so they're not as harmful as the X-rays used in hospitals. The damaging nature of X-rays can be useful too, though, in killing cancer cells. The highest energy X-rays, which are produced at frequencies in the gamma ray range, are used in radiotherapy to target cancer cells and kill them. Have you watched all the electromagnetic spectrum videos? Then you will be eager for me to complete our revision next time with a look at gamma rays. But I'm afraid there'll be no science fiction, just science fact, because
Regular review gets a better grade for you.
Don't forget to
Like,
so that I can keep making the videos,
comment,
especially to request other revision topics,
subscribe.
so you can get notifications of when my next video gets uploaded.